Przemysław Przytuła z tej strony z firmy Nowizmo. Witam na kolejnym seminarium Nowizmo dotyczącym TRIZ. Dzisiejszy temat to wiedza umiejętności uzyskiwane podczas seminarium certyfikacyjnego na pierwszy stopień. Na początku Siergiej Jakowienko, prezes TRIZ-u i profesorem IT opowie parę słów na temat tego, co dzieje się na pierwszym stopniu, jakie umiejętności i wiedza są przekazywane. Bardzo proszę w trakcie seminarium zadawać pytania i po seminarium będziemy na nie odpowiadać. Także przechodzę teraz na angielski i przedstawię naszego prowadzącego. Hello, Sergey.
Hello.
Yep, I introduced this webinar for you. We welcome you, and please a few words and start the webinar. Thank you.
All right. Hello, everyone. Good evening. I'm in Europe too, so we are in the same on the same time. I'm in Italy now. Today's webinar will be dedicated to what level 1 certification workshop will be, and what we will learn and why we learn these tools, these specific ones, and not, anything else. I'm not sure that today's participants have listened to the first webinar. Maybe there are some new people. That is why I will repeat a couple of points and a couple of slides. I mentioned before that TRIZ is a very dynamic new area of science. That it is growing, it is changing, it is developing. So TRIZ during Altschuler's time was pretty different from what it is now, because now we have a number of new tools because of necessity of new applications of TRIZ. So this slide shows the progress, the evolution of TRIZ. The first part, it was Altschuler's so-called classical TRIZ, problem-solving tools, the contradiction matrix to resolve technical contradictions, the very first variant of trends of engineering system evolution. The usual abbreviation is TESE, trends of engineering system evolution, standard inventive solutions, so tools of classical TRIZ. Trends at that time were pretty philosophical. They did not have many sub-trends or more detailed mechanisms. Now the trends are dramatically different. What was just a statement or declaration during Altschuler's time, now it has a number of sub-trends and step-by-step mechanisms that makes trends pretty instrumental now. It's still work in progress, but during the last maybe 10 years, trends, it's a part of TRIZ that have been developing very, very aggressively, very fast. When TRIZ was still in the Soviet Union, but especially when it moved out to Western Europe, to the United States, to Asia, it became clear that it is extremely important not just to attack problems with TRIZ tools, but to find problems that are new, problems that people have not tried to solve. But if we solve them, we still achieve the goal of the project. I always say that engineers think that they are married to problems. They assume that to achieve the goal of the project, they must solve this problem. And usually it is a pretty difficult one. That's why they cannot solve it easily. They forget that there may be other ways to achieve the goal of the project by solving other problems that might be easier. So a group of tools that was added to classical TRIZ in in mid 80s, late 80s, was a group of analytical tools that don't solve anything but allow to select a new problem that have not been addressed before, because this way we have more chances to generate an innovative or patentable solution. So analytical tools are like function analysis that derived from value engineering developed at GE, trimming, hybridization known as feature transfer, or even a broader way. Feature transfer is just a part of hybridization. Usually the whole method is called alternative system design. Cause effect chain analysis and the whole bunch of its derivatives like fishbone diagrams, root cause analysis, Apollo methods, all those are tools of the same category. So this combination, analytical tools and tools of classical TRIZ, problem-solving tools, they made a perfect match. It was like marriage made in heaven, because the analytical tools allowed to pull out a very new, fresh problem, and then tools of classical TRIZ showed its power finding new solutions to new problems. That's why innovative value of those solutions was much higher. Then further TRIZ deployment all over the world required pretty practical solutions, not just right solution to the right problem, but also that solution should be practical. It should have very, or as possible, short time to market. That's why later, in up to 2000, maybe a little bit even later, a group of tools was added to TRIZ that increased the practicality of the ideas that TRIZ generated. Those tools included function-oriented search and different applications on IP strategies, walking around competitive patents, developing dependent claims, finding kind of white spots on the patent map where a possibility of patenting is higher, and so on. Also, pragmatic S-curve analysis. If you read S-curve analysis in Altshuler's books, it's probably, I don't know, 3-4 pages, not more. S-curve analysis, a pragmatic one, has been booming, developing very, very rapidly. If some of you are familiar with S-curve analysis from Altshuler, you know that there are some indicators that can tell me where on the S-curve my product is, but those indicators are exclusively based on patents, those levels of inventions and so on. And that is why, those indicators based on patents produce mistakes very, very often, because those indicators only one-sided. For example, for those who are familiar with these indicators, it says that if there are a lot of patents on the system, and those patents are of kind of low level of inventiveness because all major things have been already patented, this system is at the third stage of the S-curve, pretty mature. But if I look at, for example, fuel cell systems, using these indicators, that's it. The fuel cell technology should be very mature at the third stage of the S-curve, because there are thousands of patents that are pretty low level now. So these are very typical for stage 3, but in reality, fuel cell technology is at the very first stage, because it has not come to the market yet. It just started coming to the market. How can the system be mature when the product has not shown up to the market? That's why pragmatic S-curve analysis now includes a bunch of other indicators that are not only technology-based, but also market-based. It gives a kind of multi-dimensional understanding where the system is and what kind of innovation the product requires now: disruptive, dramatic redesign, or sustaining incremental improvements. All those things are increasing practicality of solutions that we generate. And the latest addition to TRIZ, it was a bridge, a link that connected engineering with market, with generating money, because everyone heard about voice of the customer. But the point is, the problem is that very often the customers ask for things for which they're not ready to pay. And also customers ask for things that kind of they understand. And there are a lot of attributes, a lot of features that customers never ask, not because they don't need it, but because they do not realize that it is possible or those desirable features exist. So there are ways to identify hidden needs of customers about which customers have not even mentioned. And amazingly, some TRIZ tools can be used very, very successfully for this. So the process of so-called MPV discovery, MPV stands for main parameters of value, features and requirements that influence purchasing decisions. So that's a very interesting new part of TRIZ about finding unmet needs of customers. If we find those and embed them into our future products will sell like hotcakes, like iPhones. So during all these transformations and development, TRIZ changed names. In the beginning, they said, oh, TRIZ, it's classical stuff that Altshuler developed. So when we added analytical tools, we need to have a new name. And they called the combination of classical TRIZ with analytical tools innovative technology of design. It did not stick. People still continued the whole thing TRIZ, even more so because Altshuler participated in using analytical tools together with tools of classical TRIZ. There are books and there are articles where Altshuler wrote and described how to use the combination of analytical tools together with classical ones. That's why it was very easy to accept that analytical tools, it's a part of body of knowledge of TRIZ, because Altshuler participated in improving those. Then the practicality tools, when they were added, they're pretty new. And then this new combination of everything got the name of TRIZ Plus. Didn't stick. People continued calling the whole thing TRIZ. And even now, there's all these MPVs and unmet needs of customers. Again, there were attempts to call it differently, but still on the market, the whole toolkit, the whole group of all these different tools is called, TRIZ. So when we talk about TRIZ, we need to kind of understand, to clarify what people mean by that, because some people that just know Altshuler's, studied TRIZ during Altshuler's time, they think that TRIZ is just tools of classical TRIZ, problem-solving tools. Those who studied TRIZ later in 80s, they include function analysis and other tools into TRIZ. Those kind of those who studied TRIZ recently, those thousands of people from Intel or Siemens, they already have knowledge of S-curve, pragmatic S-curve analysis and function-oriented search and so on. And people that study TRIZ now, for example, General Electric started in 2006, and already there are more than 3,000 people that have been exposed to different types of training in TRIZ. They understand TRIZ as everything, including MPV discovery. So that's how evolution of TRIZ happened. And all these different tools, of course, give diversity and application of TRIZ for very different types of projects. And a lot of tools support different stages of development, right? So usually any project includes the kind of problem identification part, problem solving part, and things to do after ideas are generated, because we need to solve secondary problems. We need to take care of IP issue in case there is infringement. We can analyze newly introduced resources into the system to see how to utilize them to improve the system even more, so-called super effect analysis. So there are a lot of different tools that support product development and R&D at different stages. So a lot of tools that modern TRIZ has now. And of course, to study this, it would require 2 or 3 semesters in the university that engineers don't have. They cannot spend that much time. So to get people involved, to enable them to use TRIZ, but at the same time, to be able to handle projects right away as quickly as possible. The International TRIZ Association, that organization that was established, was founded by Altshuler. He was its first president, and he was the president of MATRIZ, International TRIZ Association, till he died. So it was his idea to develop kind of the certification system, not only for the purpose of certifying, but basically introduce a way how to bring TRIZ to people in the most rational way, to enable people to be practical and handle projects as quickly as possible. So what he did, his idea was, okay, let us learn some tools from the analytical toolbox. Let us learn some tools from problem-solving toolbox, and some things to do after ideas were generated to handle, those ideas. And that will be not exhaustive, not everything, but still, with this limited toolkit, engineers will be able to handle, quite a variety of different projects. And that was kind of the first level of the certification. And then more tools from problem identification, more tools from problem solving, and more tools to use after, like the second concentric circle. Okay, now engineers learn more, so they can do more different types of projects, can be more instrumental applying different types of tools. And of course, those who want to be like professionals, like innovation consultants, so they want to teach that in the university because, it is very popular among professors, or to be a kind of TRIZ expert in the corporate world. Okay, then they make the third iteration and learn everything that is left. So that was Altshuler's idea, and that's how he designed, basically. Well, he did not design the details, but he designed the concept of the certification in TRIZ. So there was like a pyramid. Of course, before level 1, there may be some introductory, some awareness lectures or courses, whatever, short ones. But basically, the first 3 levels of the certification, those are educational kind of levels where people learn and master tools of basic level, advanced, and professional, or sometimes it's also called expert level. There are 2 more levels, level 4 and level 5. But there is nothing to learn there. It is assumed that people that have level 3 know everything that modern TRIZ has to offer. Level 4, it is similar to, if you are familiar with different Six Sigma, for example, certification. So level 4 is like master black belt. Basically, you don't learn everything. You just perform mega projects or many projects. And level 5, it is when you do research in TRIZ and develop or improve some tool and do research. So those level 4 and 5 are not included here. Originally, level 5 people, or sometimes they're called TRIZ masters, they were just Russian ones because Altshuler was the first who kind of gave those TRIZ masters. But then gradually, again, not only Russians, joined that, but there are people from Korea, from Samsung, from POSCO. There are some people in Europe. There are some people in the United States that are not Russian that actually worked towards their TRIZ mastership and obtained those. That is kind of general facts. Now, back to the topic of our webinar, level 1, what we will learn during level 1. So if we get back to that list of different tools, that support different stages of design: analytical, problem identification, problem solving, and concept substantiation. The slide shows what tools we will discuss during level 1. Those bright yellow, that's what we should master. We should learn all the details, with all the nuances. So the only thing after workshop of level 1 that participants will need is practice, practice, practice. That's it. We have some practice, some exercises during the class, but of course, much more practice will be needed. But knowledge will be complete, and knowledge of these tools will enable the participants to be quite efficient and instrumental. So what we will learn in detail is function analysis. We will learn trimming, different rules of trimming, different types, like things like partial trimming and different recommendations, and how to choose the best new carrier of the functions when we delegate them, and so on. And as far as problem-solving tools, we will learn two major tools from classical TRIZ, the tools that were one of the first tools developed by Schuler. It is resolving problems that are modeled as engineering or technical contradictions, and resolving problems that are modeled as physical contradictions. So if some of you read, heard, or studied TRIZ already, so you might be very familiar with these tools. For resolving technical contradictions or engineering contradictions, we use the contradiction matrix. For resolving physical contradictions, we use so-called algorithm for resolving physical contradiction. So you can think, oh, those are all tools. The matrix has not changed much. There were some revisions, but nothing dramatic. Physical contradictions, no, that is from Schuler's time. You will be mistaken. Methods of resolving physical contradictions are changing. There are new ways to resolve physical contradictions, not just traditional one on separating in time, space, or relations, or system, supersystem level. Just several years ago, there was a very interesting research done, and another method was proving for resolving physical contradiction, separating contradictory demands in directions, with a group of inventive principles that are recommended specifically for this approach. So we'll talk about it in details. As for this concept substantiation or application part, we will have a little bit discussion on using TRIZ for walking around competitive patterns. There are several strategies how to use TRIZ tools for circumventing competitive patterns, and we will talk about one or two depending how much time we have. Also, there will be some introduction about tools. We will not learn the details of them, but conceptually there will be some explanation and discussion what these tools do and why they are needed and what their role is, and some general things. It is cause-effect chain analysis. Also, we will talk about evolutionary trends, because as I told you, trends are changing dramatically, and there are some kind of misinterpretation of trends that sometimes happen in books and articles. For example, what was popular several years ago is to show trends using this kind of radar diagram, like a star diagram, that is actually totally wrong. The idea about radar diagram was first expressed while Altshuler was alive, and he wrote very, very scathing, very, very angry letter about that, saying that that is a wrong approach completely. Because first of all, why do you assume that the scale of different trends is the same? Because some trends are more important, more generic than others, and one step on one trend may be equal several steps on another trend. That's why, we cannot compare. But the most important thing why radar diagrams are not true, because for a number of trends, the evolution can go both ways. in one way or another way, or the other way, depending on specific set, of characteristics of the system. That is why a radar diagram can show that, this specific system is advanced according to this trend of coordination. But advancement, moving through many steps, it means that actually that the system is undeveloped, because the most coordinated system for this specific situation is actually going from, for example, 3D to a point, coordinating action. It is not from a point to 3D, but from 3D to one point. So I don't want to go into those details without proper learning, but during the introduction on trends, we will talk what is new is developed in trends, and what is happening there. Then function-oriented search. That's a modern tool, but very, very efficient, because the major idea is why should we reinvent the wheel? Maybe there are technologies that perform functions that we need. They are in existence and they are pretty well developed, but in different areas. So instead of inventing something from scratch, let us find it existing in another field and adapt. So this way, we substitute inventive problem with adaptation problems. How to do this function-oriented search, the kind of major steps of the algorithm, we will discuss that. And also there will be introduction to standard inventive solution. Standard inventive solution, it is a tool of classical TRIZ. Sometimes people are scared about it, but actually it is a wonderful tool. I really love it. So there will be some introduction about standard inventive solutions. The workshop, basic workshop, it is 3 days. That's what minimal TRIZ requires. And we probably spend 1 day, even more, probably, a little bit more, on function analysis, because function analysis is extremely important. It's a base, it's a ground base for performing a project. We must do function analysis. And during function analysis, function analysis, as I already mentioned, it's a derivative. It's a kind of a modification of value engineering. It's a method in its own right. So it has its parts, its steps. So there are mandatory steps there: component analysis, interaction analysis, and then function modeling. Each of those steps has its rules, its recommendations, and as we learn function analysis, we will learn those rules, go through a number of case studies and examples. During component analysis, we basically identify what our engineering system is and split it into components. There are some rules, how to do it. Some things can be components, some things cannot be components. It's a mistake. So we will discuss that. And also, how to choose components of the super system, what is around my system, because I need to include those super system components into my function model as well. So after I perform component analysis, I do interaction analysis, looking what components touch each other. It's important because according to the rules of function analysis, things they don't touch, they cannot perform functions on each other. Only if components touch, there is a chance of function existence. So we will double check that. And then things that touch, that interact, we check if they perform functions on each other. Again, there is a bunch of rules how to formulate functions correctly, and it is absolutely important, very, very important, because if we formulate function incorrectly, it can lead us away from the real problem. We will choose a wrong problem, and even if we generate wonderful solutions, it will not help. So how we formulate functions, it is extremely important. So just an example, according to the rules, when we formulate functions, we need to specify function carrier. For example, the fire in this slide. it hits burgers. So function carrier, it is fire. Function recipient or object of the function, it is burger, and there is a verb, heat. So what is important here in formulating functions, the function, the verb must change or maintain a parameter of the recipient. If I cannot name a parameter of the burger that the action heat changes or maintains, I need to think again. It means if there are no parameters that the action changes or maintains, it is not a function. The function doesn't exist. It is very, very important because, in 90% of cases, of course, the way we formulate function is very similar to everyday language, but in probably 20% of cases, everyday language does not work, because in everyday language we just call functions the way that is convenient to us, but from the position of function analysis it is wrong. For example, everything about cleaning, right? If I clean teeth, if I wash windows, if I wash hands, if I cleaned the floor, that's how people usually say. But if we try to check, okay, I clean the floor, or I clean windows, what parameter of windows does the action clean change? And if you think about it, it is the same window. It is still made of glass. It is the same shape. Everything is the same. So parameter of what does the action clean changes? Oh, what it does, it removes dirt from the window. If I talk about toothbrush that cleans teeth, that's the usual answer. From function analysis, that's the wrong answer, because the toothbrush doesn't change anything in the teeth. The toothbrush removes plaque. That would be the right function formulation. When I wash hands, what parameter of the hands did I change? None. It is the same hands, the same skin, the same shape. Everything is the same. What happens? I just removed bacteria. That's the right function, to formulate. Many people can say, big deal. What is the difference? Clean teeth or remove plaque? How can it influence my problem solving? It does. Another function that is confusing, it is a function protect. We always say, oh, umbrella protects me from rain. Oh, the wall protects me from wind. Oh, coating protects the table from something. What parameter does the action protect change? For example, military helmet. What does military helmet do? And usually students give several answers. Save the soldier, provide safety, not to pass the bullet. But the most usual answer is the helmet, it protects the head, right? So the functions not pass a bullet, it is wrong, because functions are never formulated negatively. To provide safety, it's wrong. Safety cannot be a component. It is not a substance or field. It is not a material object. So usual answer that 80% of people say, it is protect the head. So helmet protects the head. So now let us check what parameter of the head does the helmet change. Some people say, oh, it keeps the shape of the head. It sounds very funny. It means if I take the helmet off, my head will fall apart. And the only reason why I'm wearing helmet is just to keep a certain shape of my head. Of course, it's wrong. Some people say, oh, the helmet makes my head hard. Of course, it's wrong. It is still the head, right? So if you think seriously, the helmet doesn't change any parameter of the head at all, right? So I need to protect my head better, because there is a complaint from the army. The soldiers, many soldiers get killed, so improve the helmet. So if I formulate the function of the helmet, helmet protects the head insufficiently. Okay, for tools of classical TRIZ, for standard inventive solutions, for example, there will be a signal. okay, there is something wrong happening between helmet and head. You know, the people are not happy. So, okay, let us use TRIZ tools to improve interaction between helmet and head, because helmet doesn't protect the head well. And then TRIZ will start suggesting, oh, you know, improve the interaction between helmet and head. And if we take this problem and solve it, you know what will happen? Yes, we design a wonderful helmet, very comfortable for the head, very nice for the head, but soldiers will be still killed, you know, in those comfortable helmets, but the soldiers will be killed. Why? Because what the helmet really does, the helmet stops the bullet. The helmet deflects the bullet. That's what the function. It changes parameter of the bullet, not of the head. And the problem, you know, why the helmets do not perform well, it is between the helmet and the bullet. That's where the issue is. The helmet cannot hold, cannot stop the bullet, and I need to work on that, not on the issue between helmet and head, right? So that's why it is very, very important to formulate function correctly. Otherwise, we assume it's a problem and we will be taken away to a totally different directions, right? That is why function protect is wrong. You know, the umbrella doesn't protect me. The umbrella stops rainwater. The wall doesn't protect me. It stops the wind, right? The coating of the table doesn't protect the table. It stops moisture or something. So if in everyday language we say protect, in functional language, it means stopping something. And there are a number of those confusing typical functions where people make mistake. So during training, we make a specific accent, pay specific attention, you know, to those confusing functions to make our function models, you know, as correct, as clean and clear as possible, right? So, so of course, the right way to formulate the function of the helmet will be to deflect a bullet. Of course, I'm talking about main function for what the system is designed, is to deflect a bullet or to stop the bullet. So when we build function model, it is components and functions that components perform. There may be useful functions, harmful functions, and we will discuss what it means and how to determine which one is which. Some useful functions also, maybe we need to check how well they are performed, because it may be a useful function, but it is performed insufficiently. It means it is underperformed, or on the contrary, it is performed excessively. It is also bad. So useful functions that are insufficient or excessive, you know, it's an issue. It's a disadvantage. So we need to document that. Right? Because sometimes people say, if the function is useful, that's it, that's okay. No, it's not okay. The function, air conditioner cools air, of course it's useful because I'm hot. When I teach a lecture, it's very hot. So I wanted the air conditioner to cool air, but if air conditioner underperforms and I'm still hot, you know, it's an issue. I need to improve that. Or if air conditioner cools air, but too much, it cools it so much that I'm trembling all over. I can catch a cold. It is an excessive performance of the function. It's not good either. So during function analysis, we formulate functions, and we determine functions that are issues, function disadvantages, the harmful ones, useful but performed insufficiently, and useful but performed excessively. So basically, that's what we have in the end of function analysis, a list of issues as well as function model, inventory of all the functions that exist within our system. So the results of function analysis, first of all, they are used as an input to other tools. For example, trimming. I cannot do trimming without prior function analysis because it's very dangerous. I can trim components without understanding what useful functions it performs, and instead of improving the system, I can damage it. Also, the results of function analysis can be used for developing innovation strategies. That's what I mentioned in the first webinar. So during function analysis, I can calculate value of every component. That would be functionality over cost. So function analysis allows me to calculate functionality index of every component. As for cost, I can get information about it from accounting, and I show every component of my system as a point on the diagram functionality cost. Looking at this diagram, I immediately can tell you if your product is designed well or not. Because if I can draw a line among those points that represent different components, and the points are residing in such a way that they are pretty close, sticking to the line, it means that your product is designed well, because it means that the more functionally important component corresponds to more expensive component. So those components that are important, they cost more. That's normal. You know, that is fair. In any company, people who contribute to company's success more, they have higher salary. So that's normal. But if the points that represent components are all over the place, what does it mean? It means a sloppy design, not good. I'm really happy about components that are functionally important and cheap. They're good. But I really am unhappy about components that functionally are not important. You know, for their functionality index is low, but they cost a lot, right? So when I put results of function analysis on this diagram, you know, I can go further. I can split the diagram into 4 quadrants, and I will have different innovation strategies for different components, depending in what quadrant of the diagram those components belong. For example, components that are in the left, right, upper left-hand corner, they are the best. You know, they are very good. They are my heroes because functionally they are very important, but they do not cost much. Components that are in the upper right-hand corner, they do a good job. Functionally they are good, but they are expensive like hell. So for these, I would use cost reduction techniques. Those components that are in the lower left-hand corner, they're cheap, not expensive, but their performance sucks. You know, I would use TRIZ to improve their functionality. And those components that are in the right lower corner, those are expensive and functionally not important. That is why usually they are doomed to trimming. You see, I even have not started solving anything, but I already have innovation strategies for different parts, different components of my product. Not the same size fits all. No, I have different strategies for different products. That's a very interesting result of function analysis. When I do a project, there will be more components pushed into my target domain, into upper left-hand corner. That is why if I draw a new line among those components, the new line will be steeper, right? Because there will be more components in my target domain. But what does the steepness of this line show? Of what is it characteristic? This angle? Actually, it is characteristic of the value of the whole system. The steeper the line is, the higher the value of the whole system, right? Ideally, you know, if it is vertical, cost is 0 and functionality is infinite. That's what is called ideal machine or ideal system. So the steeper the line, the more ideal the system is. So I can even compare, you know, how successful my innovative project was, you know, how much the steepness of this line changed. So there are a lot of interesting things and analytics that can be done around the results of function analysis. Function analysis shows me a list of different right, function disadvantages, but I'm not going. One issue causes another one, the second one causes the third one. So instead of resolving 20 of them, I will try to arrange them in lines, in chains. For this, I use cause-effect chain analysis. So instead of addressing many issues, I will address the one that is, in the very, very end of the chain. If I resolve it, the whole pyramid of issues will collapse. So also doing cause-effect chain analysis opens very new opportunities for me, to different type of solutions. During level 1 class, there will be just an introduction to this method, but just give you some example that has been used for a number of years. It's very simple and clear. For example, I woke up in the morning with a headache, and usually the simplest, this quick and dirty solution will be to take a pill, for headache. But of course, if I have it every morning, I would ask the question, why am I having headaches? I go to the doctor, examines me and says, well, that's clear, because you have high blood pressure. So if in the very beginning I had only one solution, to take a pill for headache, now I have another solution. I can take medicine to decrease my blood pressure. But I can continue asking my doctor, why do I have high blood pressure? I never had it before. The doctor says, okay, let us take more tests. And the blood test shows that high blood pressure is driven up. I have it because of a high concentration of salt in my blood. Oh, it gives me another solution on top of what I already had. I can take medicine to normalize the salt concentration in my blood. As the result, the blood pressure will normalize, and as the result, I will not have headaches. But I can continue asking doctor, well, I never had that issue with salt in the blood. Why now? Well, the doctor explains, you eat a lot of junk food, so switch to a healthy diet. Here we go. I have another solution. Long term, I can switch to a healthy diet. As the result, the salt will normalize. As the result, blood pressure will normalize. And as the result, I will not have headaches. So you see, I have different types of solutions: short term, long term, more kind of fundamental one, and so on. So I have things to choose from. Right, and I can continue. So this method has different also rules from where to start this cause-effect chain, when to finish. Sometimes it's not change, but a circle, so-called vicious circle. What to do in those cases. So that's what cause-effect chain analysis is. So usually, the very first the starting point, it is so-called initial or target disadvantages, and then asking questions, why. We go down the chains to discover those issues that are underlying at the very beginning of the chain, because those we should attack. Not the initial one, not the intermediate ones, but those that are in the very, very basis level. Because those that are on top, people have already tried to resolve it. The deeper, with why we go, the newer the problem will be, and the better chances we have to generate some innovative solutions. Another tool that we learned during basic training in detail, in every detail, will be trimming. So trimming means removing components associated with issues. That's a very unusual approach, because usually engineers try to fix things and they don't think about throwing components away. So that's what trimming does. It is removing some components that give us headache from our system, but because prior to that we did function analysis, we know all the useful functions the components perform. That is why we preserve the useful functions by delegating them to system, remaining system, and super system components. All right. A quick example, that's the one that I had in 1997 in Japan at Honda. We generated a solution, patented it. They even included me as a co-author of that patent. That was about the gas tank of Honda motorcycle. It was too big. They tried to optimize it and did not get any good idea. So when they heard about trimming, they really loved the approach. So they built function model of that motorcycle. Because there was issue with the gas tank, trimming suggested that instead of improving or optimizing the gas tank, let us throw it away. We can do it, but the gas tank performs some useful functions. It contains gasoline. So I can throw out the gas tank if the function is performed by something else. I need to teach the remaining parts of the system to perform the function to contain gasoline. And what the team did, they trimmed the gas tank and delegate the function contain gasoline to the frame. So now they need to find a solution how to enable the frame of the motorcycle to contain gasoline. For that, they even did not need any problem-solving TRIZ tools. Brainstorming immediately gave answers. So on that slide, you see very different modifications. Right now, there are a number of designs of motorcycles and motorbikes that do not have the gas tank. Actually, they have it, but it is combined with the frame. The frame is hollow and it is filled with gas. But the very first patent on that, it was our patent at Honda in Japan. So that's a very simple and very exemplary kind of case on trimming. But it is more sophisticated tool. There are a lot of different details, as I told you, partial trimming and so on. All that will be discussed during level 1. And two problem-solving tools. When we model our problem that came from trimming, for example, as a technical or engineering contradiction or physical contradiction. These are two different problem models. If we model our problem as engineering contradiction, there is a tool that understands the language of engineering contradictions. That's contradiction matrix. If we model the same problem as a physical contradiction, there is a tool that understands physical contradictions. It's this algorithm for resolving physical contradictions. So as for engineering or technical contradictions, that. It's kind of trying to optimize between two parameters. Improving of one parameter leads to deterioration of another parameter. And usually what people do, they optimize. They try to find a compromise. A lot of different optimization methods, including, favorite of everyone, Six Sigma, and so on. But when we optimize what we have, we find that balance. But as the result, none of these two parameters really reaches the level that we need. When we use the contradiction matrix, the tool that resolves the contradiction, engineering contradiction, not kind of optimizes, we get a picture when improving on one parameter does not jeopardize the other, and sometimes actually improving on one parameter improves the second parameter either. That is very, very counterintuitive. Sometimes engineers even don't believe that it is possible. But using a contradiction matrix and the inventive principles that the contradiction matrix recommends, can help us to achieve it. The matrix doesn't give us a ready solution. We still need to brainstorm around the recommended principles, but still the heuristic value of the recommended principles is a matrix of the matrix is still amazing. So we will talk about the matrix, about the inventive principles, more details, some practical things that we can squeeze out of the matrix. All this will be discussed in every detail during the basic course. And resolving physical contradictions. Yeah, it is described in books, separating physical contradictions in time, in space, in relations, system, supersystem level. But as I told you, there is a new direction now, separating contradictory demands in directions. And also there are methods of satisfying contradictory demands, and there are methods of bypassing contradictory demands. All these things were published in the one of the latest Altshuler's article. Altshuler was a co-author on that. That is why the authorship of methods of resolving physical contradictions or satisfying them or bypassing them, it still belongs to Altshuler. Physical contradictions, for those who don't know, it is when we have two opposite contradictory demands, justified demands, placed upon the one object. Something should be thick and thin for a reason, something should be transparent and opaque for a reason, something should be big and small. So those models of the problem as a physical contradiction sound real, like a miracle. We cannot solve it. The hammer, the hammer should be heavy to drive nails very efficiently. But if I work with heavy hammer, I get tired, then the hammer should be light, so I will not get tired. So I have two opposite contradictory demands for the hammer. It should be heavy to drive nails better, and it should be light, so I will not get tired. How to resolve that? That's impossible. But it is possible because TRIZ has these methods of handling physical contradictions. Three big groups: separating contradictory demands, satisfying contradictory demands, and bypassing contradictory demands. And there are more detailed kind of sub-methods within each of these groups. Separating contradictory demands, I can separate in time, space, relations, directions, and so on. But also I can satisfy contradictory demands and bypass them. So there are many details. There are a lot of new things, from recent development. And depending what direction we choose, separating in space or separating in time, or at the system level, there are several inventive principles that are specifically recommended for that or another direction. And again, we use the inventive principles to brainstorm around the solution. So we will spend specific time about discussing new stuff, separating contradictory demands in directions, and inventive principles that are the most efficient, for separating contradictory demands in directions. In this direction, the glass is permeable for bullets. In this direction, it is not permeable. Actually, that's one of the modern ideas, because when the policemen are chasing criminals, they should be able to shoot sitting in their car without leaning out of the window. It means that the windshield of their car should be permeable for bullets. But if someone is shooting from outside in, the windshield should be impermeable. So basically, the only way to resolve this situation and to generate a pretty innovative idea was to use the separating contradictory demands in directions, because in one direction the window should be permeable, in the opposite direction the window should not be permeable. A very interesting way to separate contradictory demands in satisfy contradictory demands. I hope you can see this picture. I know it goes with a little bit delay. So if you see this picture, there is a lady here, and I usually ask the question, is this lady old lady or it is a young and pretty lady? And different people look at the same picture, and some people say, no, it's an old lady. You see a big nose and gray and this, protruding chin. And some people say, no, it's a young and pretty lady, with a nice hair, and some people say both. Because, if you look at this picture attentively, you can see both lady. It is a young lady that is looking somewhere aside, so you just see her, ear, or it is an old lady, with a big nose and so on. Basically, it is satisfying contradictory demands. It's old lady and young lady in the same picture. And the last thing we'll talk about, level 1 workshop, it's a couple of strategies for IP when we use TRIZ tools. So there are a number of typical patent strategies, invented by not by TRIZ but by patent lawyers, but they can be enhanced. They can be given a different twist, improved, intensified using TRIZ tools. Of course, that's a topic for a separate workshop. We can talk for a couple of days about that. But during level 1 workshop, we will talk about 1 or 2 strategies of circumventing competitive patents. But also, there are strategies for developing dependent claims, white spots, developing firewalls, and so on. So that's pretty briefly what level 1 class will include. So I know I'm a little bit late. But that's all I wanted to share. So if you have any questions, I will be more than happy to answer. Thank you.
Okay. Thank you very much. We have some questions. First one is about specific applications. Is it good for aviation enterprise? Do you have any examples for aviation?
Of course, aviation. What's wrong with aviation? I'm kidding. Well, first of all, companies that are pretty much in aviation use TRIZ very, very intensively with very good results. The first thing, GE Aviation. Because the programs, TRIZ programs at GE keep on going. So GE Aviation in Cincinnati, GE Aviation in Global Research Center in Bangalore in India, number of groups, they work on aircraft engines. They are using TRIZ, very successful, number of patents. Boeing used to use TRIZ pretty intensively. I was involved in some programs there. But also we did things together with another TRIZ master, Zinovy Roizen, a company that in the past was called Boeing Rocketdyne. This is a part of Boeing that was developing the engines for spaceships. Several years ago, Boeing Rocketdyne, that was very, very strong in TRIZ. There were TRIZ teams there. It was acquired by United Technologies, but it is still there. It is still working on airspace engines. Then Lockheed Martin. Lockheed Martin also has 3 or 4 internal TRIZ experts that basically do TRIZ projects exclusively. So that is why aviation, it is a very good application of TRIZ. Also Bell Helicopters, Sikorsky, all those companies had number of TRIZ programs pretty successfully.
Yep, great. That's a great answer. Lots of applications there.
Also, some time ago, there is this JPL Jet Propulsion Lab. There are also TRIZ educated people that use TRIZ from now and then in their projects.
Okay, I have another question about someone reading on our page that CEO of Samsung has TRIZ level 1 certificate. Is it true?
CEO of what Samsung? Because Samsung, it's a conglomerate of different companies. There is Samsung Electronics, there is Samsung Display, there is Samsung Semiconductor that are part of electronics. So there are different Samsungs. So that's why I don't know. I know that that president of Samsung Display, he attended the level 1 training and some special topic workshops. That I know because I did that training. So, but as for other CEOs or presidents of other divisions, other companies of Samsung, I don't know. The very first exposure, and that's why Samsung was so active with TRIZ, that was because the chairman of the board, loved TRIZ, former one, not the current one, but former one. I'm not sure he knew TRIZ, but he loved it definitely.
Okay, great. Let me see if there are some other
The
questions.
head of vice president, senior vice president of GE, Mike Idelchik, he attended level 1 workshop. Also, the head of the technical center in Bangalore, he attended level 1 workshop.
Yeah, okay. Thank you very much. We have another question. It's about the craziest project you ever done with trees.
The craziest, in what sense the craziest? The most unusual project that kind of, what do you mean by the craziest?
I don't really know. Maybe let's assume this is the this meaning.
Well, the most unusual projects, it is usually with products that are very regular, mundane, something that I use every day and consider this product very simple. So if I change dramatically there, that amazes me. If I find some super duper technology and I use this technology in improving aircraft engine, it is just normal. Okay, yeah, I know technologies can do a lot of things, but to really improve a very simple product, that is the most difficult. I always say that it is much easier to improve aircraft engine than to improve a regular bucket, because the bucket does not have resources. You cannot use some sophisticated and expensive things, and the product has been around for centuries. That's why it's very difficult to think about really something new. So to tell the truth, my personal opinion, the most impressive projects I had, really, they happened during TRIZ programs at Procter & Gamble, because Procter & Gamble products are very diverse. It is consumer products, it's oral care, it is personal hygiene, it is feminine care, diapers, it is food and beverages, it is packaging. So the diversity of projects is amazing, and probably the most impressive things happened to me there.
Yeah, thank you very much. I don't see any questions on the chat. Let me check again. Okay, I think that's it for the questions.
All right, then just the last sentence. So they have one more webinar schedule. It's basically about TRIZ for some newer applications. TRIZ for innovative logistics, for streamlining supply chains. It is TRIZ for entrepreneurship, different aspects of that. TRIZ for the Internet of Things, and so on. That would be the topics of the next webinar.
Yeah, great. Thank you very much. I will just switch to Polish.
Right. Okay. Thank you, guys. Thank you. Bye.
Thank you. Drodzy Państwo, bardzo dziękuję za uwagę dzisiaj. Zachęcamy do zadawania pytań profesorowi, tak aby mógł poruszyć na tym albo na kolejnych seminariach tematy, które Państwa najbardziej interesują. Na dzisiaj to wszystko. Zachęcamy do zadawania pytań i do następnego seminarium, które odbędzie się za tydzień 14 czerwca, również o godzinie 20. I tak jak profesor powiedział, tematyką będzie stosowanie współczesnego TRIZ-u. Jeżeli mają Państwo jakieś pytania, bardzo prosimy wysyłać je do nas na biuro@nowizmo.com. Postaramy się przygotować tak, żeby na webinarium te tematy były poruszane. Jeżeli mają Państwo różne inne propozycje na naszych webinarów, również prosimy je wysyłać. Ja w tej chwili Umieszczę jeszcze raz adres mailowy na czacie, tak aby nie było pomyłki. Dzisiaj to wszystko. Bardzo dziękuję Państwu za uwagę. Miłego wieczoru. Do widzenia. Do usłyszenia. Thank you, Sergey. Bye.
Bye.